Okay, so if we talk about combining volumes of gases, okay, Gay-Lussac analyzed chemical reactions that involved gases. Okay, he studied the volumes of the gaseous reactants and products and concluded that gases combine in very simple proportions. So, the law of combining volumes states that when gases react, the volumes of the gaseous reactants and products is measured at constant temperature and pressures are always in whole number ratios. So what this is saying, for example, we have nitrogen gas plus hydrogen gas is going to give us ammonia gas. Okay? This is in a 1 to 3 to 2 is the volume of the ratio. So for every 1 mole of nitrogen gas and 3 moles of hydrogen gas, 2 moles of ammonia gas is produced. Okay? The formula that we have here is, okay, that it is this idea of volume, this ratio of volume to moles. Okay? We look at these as the balancing coefficients. As an example here, the example is the volume of nitrogen is used up, what volume of nitrogen is used up if 100 milliliters of ammonia is formed in a composition reaction. So we need to compare the ratios of volume, so coefficients for what values you know and what values you are solving for. So in this case here, we have, this is the level of reaction we're talking about, this 1 to 3 to 2. Okay? So, we do not know the milliliters of nitrogen. All we know is the milliliters of ammonia that we're going to get out. So we have this formula here. Okay? So, again, I would like to see this underneath this equation here is what you know. Be more specific about what you don't know, okay, before putting your volume in. We know that X milliliters is going to equal to so many milliliters over this 1 to 2 mole ratio, okay? And because of this, we know we're going to get 50 milliliters, or the volume of nitrogen that's used up is 50 milliliters of nitrogen. Now, if we look here at ideal gas law calculations, this law combines all 4 variables of pressure, volume, moles, and temperature into one equation, okay? And this equation is PV equals nRT, okay? This is a very, 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 very important formula, okay? Where V is volume in liters, T is temperature in Kelvin, P is pressure in kilopascals, N is the number of moles in mole, so that is the units that we're using, and R is the universal constant, which happens to be 8.314 kilopascal liters per mole Kelvin. So, in this case, for example, what is the volume of 10.8 moles of oxygen gas at 100 kilopascals and 15.5 degrees Kelvin? Okay, what do we know? Well, I know the number of moles, I know the temperature, there's my conversion over here to Kelvin, I know how many what the pressure is in kilopascals, so I don't need to do any calculations there. I know my constant. Again, I would like to see the volume is equal to question mark, or this is what you don't know. Okay, here's my formula. Here's my substitution. Okay, if I manipulate the equation around such that I solve for volume, I'm going to be given 259.1 repeating liters, and for proper significant figures, 259 liters. Okay? Another example, a rigid steel vessel with a volume of 20 liters is filled with nitrogen gas to a pressure of 20,000 kilopascals at 27 degrees Celsius. What is the number of moles of nitrogen? Great question. Here are the things that I know. Okay, I know my temperature. I know my volume. I know my pressure. I know my constant. Okay, I'd love to see, what am I trying to find out? Number of moles. Here's my equation. My substitution and my manipulation would give me this answer. Rounded to proper significant figures is 160 moles. Here's my third example. What I would like you guys to do is to do this example on your own and be able to check this one in the next video coming up.